All right, let's go ahead and do this last piece. Right, so part 3 is on vectors and vector operations. There's a few that we need here, and I'm going to keep referencing them. They're all here. Right, here's transpose, we'll need this. Here's dot product, we'll need this. Addition, subtraction to find how you would think. We have cross product, and the magnitude, right, is the norm. So everything is here, right? These are all the instructions that you'll need as far as manipulating vectors. We also have down here plotting 2-dimensional vectors and plotting 3-dimensional vectors. I'm going to do the 2-dimensional one with you, and you'll be left with the 3-dimensional one. Right, so part 3 exercises, recall, etc. Right, A, B, C, and D. We already have that from above. We never cleared that out. And so we're on to 3A. Right, it says magnitude and unit vector. It says consider the two-dimensional vectors given below, then perform the indicated operation. So before we begin, we need to first define what V1 and V2 are. So we need to define some vectors in our MATLAB. So let's go down here. And again, I left this for you guys. I'm going to clear this or else it's not going to like this. Because I've left R2 defined abstractly. So you do have that last part of 2 to do. I guess it's just 2. There's no 2A. This is 3A. And so we first need to define V1 and V2. So V1 is going to be equal to, with a vector, we're putting a bracket. We have A plus 2 to B minus 5. Here's our first one. We don't want an output. And same thing, V2. And we're going to set it equal to C plus 7 to D minus 15. So we've defined the vectors now. Let's see what else we want. So let's go ahead again, control save. I know it seemed really dumb. We're going to run it. And it runs fine, right? Same idea. And so let's go back now. So it says find the magnitude of V3. So first we just needed to declare what V3 is, and it's a scalar multiple of, or a linear combination of V1 and V2. So 2 times V1 minus 3 times V2. So we'll say V3 is equal to 2 times V1. Remember, you need the multiplication. Minus 3 times V2. We don't want it to output, so just semicolon. Control save. Again, you can run it. I'm pretty sure my code's going to run. I'm going to move forth. I think it also says we want a V4, right? It says using the distance definition with the square root and 2 with norm already built in. Declare these. Next, find a unit vector. Okay. Okay, so let's, you can define, just to keep it the same, I'm going to define V4 and then we'll go back to what this is. So define V4 as well, which is at the bottom, which is just V1 plus V2. I just want to get that out of the way. Then all my V1 through V4s are all together. Okay. So P3A1, so now it wants us to go through and find the magnitude, right, using the norm operation and also the square root operation of the distance function, right? So as long as we know the definition of the magnitude, we should be good, right? Of course, I'm going to remind us here. So we'll say P3A1, P, capital P, 3A1 is equal to, right, the square root of, well, remember, the magnitude of a vector is the square root of all of its components squared, right? So in this case, we're going to say V3, 1, right? This is saying go grab the first component of V3, and we're going to square it. And we're going to do the same thing again. Go grab the second component of V3, and we're also going to square it. And I already have this locked in the square root. Right, so there is just the definition of the magnitude. Right, I'll control save. Let's go ahead and run. I did have it output now. We can see. I know the charts keep running. Now P3, so P3A1, this is the magnitude of the vector. And we also have a built-in function. So it's saying P3A2 is just going to be equal to norm of V3. And I'm going to let these both output for right now because I'm going to double check that these should be equal, right? And we can see after we get rid of these charts that they are indeed equal, right? Showing that the definition of magnitude and the built-in function should give you the same output. Okay, so I think that takes care of, oh no, we need one more part, right? we need the unit vector, right? Well, we know for a unit vector, right, all that is, and I think we call this P3A3, so it wants a unit vector of V4. Well, that's just going to be the vector V4, right, divided by the magnitude of V4, which we can use the norm call. And again, control save, we'll go ahead and run. Right, so we have the unit vector here of V4, right? So here's 3A. I'm going to do 3B and 3C with you. So let's go ahead, we'll do 3B, right? So it's just testing us on these operations with vectors. I think we're going to use the same vectors we already have there. Let's go back. So 3B, the algebraic dot product. Consider the same two-dimensional vectors, V1 and V2, which we've already defined above. Find the dot product of these two vectors two different ways in MATLAB using the standard definition where you multiply the first vector by the transpose of the second vector. Okay, so let's start with that. Right, so using the definition, so that's what we did with the magnitude, right? We use the definition, then we use the built-in. We're going to do the same thing here with dot product. We'll use the definition, then the built-in. Right now, it's kind of hard to show here, but in order to multiply two vectors together, right, we have to have a row vector and a column vector, right? So if we define, let's go ahead, we'll write P3B1 for right now. Right, we're going to say V1. Well, V1, I believe here, let's think about right, this would be defined as a row vector. If I leave it as is, V1 is what's called a row vector. So just imagine the vector horizontally. Times, well, now I need to define the other one as a column vector, V2. Now, in our instructions, the way that we do this is by putting this little apostrophe, right? This tells us to transpose the vector. Now, if you don't do this, your code won't be able to run because it's going to say you have the dimensions won't line up, right? Now, remember, when we do a dot product, we get a scalar. And again, we can double check our answer here to make sure that what we did is correct because there's also the built-in, which is just known as the dot between V1 and V2. And so these answers should be, oh, I don't want that. Let's control save, and then we can run. And again, sorry, once I get rid of the graphs, I can see that P3B1, P3B2 are exactly the same. All right, so that is all of 3B. And again, I'm going to do one more part, and then I got to leave you with something to do for this. Let's go back to the instructions. Again, I know I'm talking fast, so feel free to pause the video. I'm trying to make these in under 10 minutes. But feel free to pause the videos, rewatch them. Let's look at 3C, geometric dot product. Consider the same two-dimensional vectors, V1 and V2. Plot each of V1 and V2 on the same axis using the hold on. Right, all of this is defined above. So if you're like, what is hold on? We could go up here, and we could go find an example of hold on. Might be a little bit further up. Let's read the rest. Hold on. Both beginning at the origin. Figure 5. Next, determine the angle between the two vectors using the proper operations discussed from lectures, right? We had two that we could have used, right? The sine of theta, right? We said sine of theta is equal to the dot product divided by each of its magnitudes multiplied by each other. So we're going to do 3C, and then I got to leave you with 3D. There's not a whole lot of difference here, right? 3C is just 2 dimensions. 3C is 2 dimensions. 3D is 3 dimensions. Right, if you scroll up a little bit, you'll notice plot vectors in 2D, quiver, plot vectors in 3D, quiver 3. So it's all right there for you. Let's go back to our 3C, right? So I can immediately, I've already defined my vectors, right? So I can immediately go to my figure 5 and say, well, I'm going to go ahead and go quiver. And let's do one of my vectors. We'll use V1. Now I'm starting from the origin, right? So this is my starting place, 0, 0. And now my ending place would be V1 of 1, right? That's my x component, and V1 of 2. That's my y component. And now what it's saying is you've plotted one of your vectors, right, V1. However, you still want to go plot your other one. So we need to hold on. Don't do anything yet, because if you leave, right, then it's not going to plot the other vector. And guess what? We're still in 2 dimensions, so I still need quiver, just quiver. And we're going to do the same thing, right? 0, 0, my starting point. And then I want to go grab my x component of v2, and I want to grab my y component of v2. And I think that is it for the quiver process, right? So this should give us a graph. Let's go ahead and control save. Now there is one more part to this, right? So there's what our figure 5 should roughly look like, and now it wants us to find the angle between these two vectors. And so from lecture, we have, we'll label this P3C right now. This is going to be, right, remember, maybe I'll go over to my notes here, right? Remember, it's cosine of theta, and I want theta by itself. So imagine this is like theta over here. P3C is theta, which means I need to do arc cosine of theta of the dot product, right? So the dot of V1 comma V2. Let's make sure I have this right. There's the dot product divided by, and I need to put in parentheses here, right? I need the norm of V1, or the magnitude of V1, times the magnitude of V2. And let's control save, and we'll let that output. And let's see what we get. I know we got figure 5, figure 3, figure 1. So I got half the figures there for you. And we can see this is, apparently it's a very small angle, right? Very small angle between the two. Very close. So I'll leave this there for you. That takes care of what I'm going to go through. I think I've done probably about half the code. And I'm going to keep this under 12 minutes. So I'll see you in class.